Right, hello everyone. So this is the derivation for Bernoulli's equation. So this was discussed briefly in the lecture notes, but I'm going to go in a little bit more depth here. So what we want to consider in this situation is our cube of fluid that is moving along this streamline that has a path length S. So essentially what we're going to do here is consider the change in pressure at two positions on the cube. So we've got the leading edge of the cube here, and we've got the trailing edge of the cube here. So we say that the cube has a side length L. So obviously the volume of the cube is L cubed. The face of each side of the cube, so the leading edge and the trailing edge, is going to be L squared. And we say that at the centre point of the cube, our fluid has a pressure P. So what we're interested in is the sort of pressure difference across the cube. So what we want to consider is the pressure at the leading edge of the cube is P, the pressure at the centre, but then we have this additional term here, dP over ds, that is the change in pressure as it moves along the streamline, basically the rate at which it moves along the streamline, and this is at a distance L over 2, so half the distance of the cube side from the centre. So the front face, the leading face of the cube, has an increase in pressure. The left-hand side, the trailing phase, has a decrease in pressure by the same amount. So this term here, dP over ds times L over 2. So what we're interested in is the net force exerted on the cube. So we can say that force equals pressure multiplied by the area. So in this case, the area, as I said, is L squared, and the pressure is the pressure difference between the two sides. So the force exerted on the cube here becomes the pressure minus dP by ds times L over 2. So that's the pressure term multiplied by L squared, and then less the pressure on the leading edge. L squared. Okay, so this is our force term here due to the pressure, but we also know that we can rewrite the force as F equals mass times acceleration, and we can say acceleration is du by dt, where you use the velocity of the cube along the streamline. So we can say this term also equals m du by dt. Okay, now we have a mass term in here, and this is a volume of fluid. So the mass equals the density of the fluid multiplied by the volume, where this volume term is going to be L cubed because it's a cube. So we substitute these this term in here. So we substitute density multiplied by L cubed for mass in this above equation, and this means we have P minus dP by ds L over 2 times by L squared minus P plus dP by ds L over 2 multiplied by L squared again, and we substitute in rho, then L cubed du by dt. Now for each of these terms on the left hand side, we've got an L cubed term, so we can cancel out all the L terms, so the size of the cube no longer matters. And then we can do a little bit of rearrangement and cancelling. So again, we've got a pressure term here, and we've got a pressure term that's subtracted here, so those two terms cancel out, and then we essentially have minus a half dP by ds minus another half dP by ds. So this simplifies down to dP by ds equals, this is minus dP by ds equals the density times du by dt. Okay, now we do a little quick bit of manipulation here, which is to say that du by dt can also be expressed as du by ds multiplied by ds by dt. Obviously here the ds terms would cancel, so this is still du over dt. And what the thing to recognise here is that ds by dt, this is u, because it's as we travel along the streamline, ds by dt is the velocity along that streamline. So this means that we can rewrite du by dt as u times du by ds. Okay, so we can substitute this back into our equation here, and then we have minus dp equals density times velocity du by ds. Oh, sorry, that should be ds over there. And then the ds's on either side cancel, and this means our equation becomes dp density u du. Now in the lecture slides and in the textbook here, there's a bit of identity manipulation done, which is to say that du squared equals 2u du, and then the integral's done on the basis of that. I find it slightly simpler just to work with what we've actually got here. So we'll just integrate between two arbitrary points along our streamline, which we'll call position 1 and position 2. So what we end up with is an integral between pressure at point 1, pressure at point 2, this is minus of dp, equals rho, integral between velocity at point 1, velocity at point 2, u du. So in the textbook version, they've substituted in a du squared term, and this u disappears, and there's a half under the density. And then this means that we end up with P1 minus P2 equals a half times the density U2 squared minus U1 squared. And then if we rearrange a little bit, we'll bring the density across. We get P1 over density minus P2 over density equals a half U2 squared minus half u1 squared, and then we can bring the 1 and the 2 terms to the same side. So what we have is p1 over density plus half u1 squared equals p2 over density plus a half u2 squared. Okay, so because we've chosen positions P1 and P2 completely arbitrarily, we can say that what this tells us is that the pressure over the density plus a half times the fluid velocity squared must be a constant at any point along the stream tube. And this is the basic version of Bernoulli's equation, where we've assumed there's no elevation change of our streamline. If we factor in an elevation change, then we simply add in a term related to the height difference at any point along the tube. Okay, so this is the Bernoulli's equation derivation, and in the lecture notes and in various points you'll see this is quite a useful equation to know. Okay.